In this video, we are going to conclude the series of reactions that are involved with aldehydes and ketones. We are now going to focus on looking at sulfur nucleophiles. Ketones and aldehydes, understand that are going to be reacting with thiols virtually the same way that they react with alcohols. So, earlier in this chapter, we saw how alcohols, when they react with aldehydes and ketones, are going to be forming an acetal. So, if now the molecule that we are interacting our aldehyde and ketone with is a thiol, then what we're going to be forming is a thioacetal. Understand that this reaction happens under acidic conditions. You can see in the second reaction in this slide that we can also have a dithiol also present in order to react with our aldehyde and ketone, and what that is going to result is into a cyclic thioacetal. Thioacetals can be converted into alkanes when we reacted with Raney nickel. Okay, this is just a very specific reaction. Okay, now understand that this allows for another method for reducing a ketone or an aldehyde to produce an alkane. We, in the previous video, learned about the Wolff-Kishner reaction, but now understand that there's another way to convert particularly a ketone to an alkane, and that is with the use of a thioacetal followed by a second step with Raney nickel. Now, remember that aldehydes and ketones are reduced to alcohols with a hydride reagent, meaning lithium aluminum hydride or sodium borohydride function as a hydride delivery reagent. And as you can see here, depending on what we start with, if it's an aldehyde or a ketone, if we start with an aldehyde, then we're going to be forming a primary alcohol. If we have a ketone, then what we're going to form is a secondary alcohol. Now, understand that these reactions are carried out under basic conditions. Okay? Hydrides are actually strong nucleophiles. Now, remember that the reduction specifically of an unsymmetrical ketone, if it results in the formation of a chiral center, is going to be producing a racemic mixture. So as you can see here, the ketone that we have, which is 2-butanone, when it undergoes reduction with lithium aluminum hydride followed by water, it's going to form a chiral center, okay, specifically at the carbon that used to be the carbonyl at this position. So once the reduction happens, understand that we're going to have a mixture of stereoisomers. And again, that introduction of that process is part of the hydrogen nucleophiles. Let's now explore carbon nucleophiles in our system. Now, understand that Grignard reagents can attack aldehydes and ketones to make an alcohol, but more importantly, not only we are going to form an alcohol, we are going to, in addition of the alcohol, make a new carbon-carbon bond. So understand that there's two things that we have to have in consideration with this reaction. So, for example, if we have a ketone or an aldehyde, and as you can see, the examples that we have here, in the first one we have cyclohexanone interacting with methyl Grignard. What we're going to have in the highlighted portion is the incorporation of that methyl group. So we have a new sigma bond, but we also have the formation of the OH group. Remember that this reaction every time is 2 steps. Because after the incorporation of the Grignard, we need to protonate that oxygen that forms as an intermediate. In the second example, as you can see, that's an aldehyde specifically interacting with our Grignard reagent. And again, when that occurs, pay attention that when you are forming these groups, if you form a chiral center, we're going to have a compound that is going to form a racemic mixture. Now, understand that either phase of the carbonyl is attacked by the nucleophile. So, in the case that we form a new chiral center, we are always going to form a racemic mixture. So, when it comes to the mechanism for the Grignard, it's pretty straightforward. In the first step of the reaction, our Grignard reagent is going to be acting as our nucleophile and is going to attack the carbonyl group. Then we are going to form an intermediate in which our oxygen atom is negatively charged. Make sure that you follow the flow of electrons. And the reason why we have that second step of water is because understand that that alkoxide ion that was formed after the attack of the Grignard reagent needs to be protonated in order to form the alcohol. Now, this reaction that we're going to discuss now is called the cyanohydrin formation. Understand that the cyanide ion is also a carbon-based nucleophile, and reversibly it acts to ketones and aldehydes to form a group that is called a cyanohydrin. So whenever we have ketones and aldehydes interact with hydrocyanic acid, what we're going to form is a cyanohydrin. Now, this reaction works better under basic conditions, so a catalytic amount of base is usually utilized. This is the mechanism for the reaction. Now, understand that in the first step of the reaction, we are going to have our cyanide ion function as a nucleophile and attack the carbonyl group. Once that happens, then as usual, once the attack occurs at the carbon and the carbonyl, the electrons are going to move, I should say, to the oxygen atom, and is going to make that oxygen atom negative. In the next step of the reaction, we are going to have HCN protonate the oxygen atom, and that's what results in the cyanohydrin. Now, that acidic workup is not necessary since HCN itself can going to be serving as a source of protons, so we don't have to add extra acid to the system. So, to achieve basic conditions for the cyanohydrin formation, understand that we are going to have potassium cyanide usually added along HCN in order to accomplish the reaction. Okay, as you can see, In this way, there is going to be more cyanide ion present in the reaction than protons because of the hydrocyanic acid. Now, understand that a new chiral center is possible in this reaction as well. So always pay attention depending on the molecule that you're starting with. If it's going to form a racemic mixture, it is always going to depend on what you start with. If it's an aldehyde or a ketone, and after the incorporation of these groups, if we're going to have 4 different groups attached to the carbon atom. Understand that the installation of that cyano group is advantageous because it can be converted to other functional groups. So as you can see in the first reaction, once we have that cyano group incorporated into the system, it actually can be converted into a primary amine when we reduce that cyano group with lithium aluminum hydride. The lithium aluminum hydride is going to convert it into the amine. Now, that cyano group, as you can see, if we put it with acid and heat, it can actually be converted into a carboxylic acid. So it gives diversity to the type of functional groups that we can form in this reaction. Next, we are going to be observing and studying the Wittig reaction. When it comes to the Wittig reaction, understand that this is an extremely important reaction in organic chemistry, just like the Grignard, because the carbon skeleton is going to be modified. So, when it comes to the Wittig reaction, ketones and aldehydes are going to be converted into an alkene with the formation of a new carbon-carbon double bond. So, as you can see in this reaction, if we start with an aldehyde or ketone, when it interacts with the Wittig reaction, and we call it Wittig just because of the pronunciation in German. So, in this Wittig reaction, this Wittig reagent, I should say, what it's going to be making possible is that the oxygen atom in our carbonyl is going to be replaced by the carbon that is part of that Wittig reagent. Okay, so here we just have 2 examples of the reaction itself. So understand that that Wittig reagent that I mentioned in the previous slide is known as a phosphorus halide. That's how you pronounce that word. And this phosphorus halide is what's going to be acting specifically as a nucleophile. Understand that an halide is going to be a neutral compound that contains a negatively charged atom adjacent to a positively charged heteroatom. So the mechanism of the whole system is likely to have a 2+2 cycloaddition between the Wittig reagent and the carbonyl group. So exploring the reaction mechanism for the Wittig is going to be as follows. The Wittig reagent specifically is going to react by a carbonyl group through what we call the cycloaddition process. The carbon atom that is part of the Wittig is going to attack the carbon in the carbonyl, while the double bond in the carbonyl is going to attack the phosphorus. Then, as you can see, this is going to make an intermediate. As you can see, this is the name of the intermediate. Some of these intermediates have some weird names, so you don't need to memorize the name of it. But please note the structure. So it has this 4-member ring intermediate, And what happens is that that intermediate is going to decompose by, let me just highlight specifically the arrows. The phosphorus carbon bond is going to go down and make the carbon carbon double bond, and then the oxygen carbon of the carbonyl bond, that sigma bond, is going to break in order to put that oxygen with the phosphorus that was part of the Wittig reagent, and understand that that overall is what is going to be producing the alkene, and in its turn is also going to produce a triphenyl phosphine oxide compound. That's how the oxygen is removed in the system. So understand that the formation of the specially stable triphenyl phosphine oxide byproducts is what drives the equilibrium to favor the formation of the desired alkene for the reaction. So understand that a given Wittig reagent is synthesized in two-step from the corresponding alkyl halide. And as you can see, these are going to be the steps in order to be producing the reagent itself. We're going to have an alkyl halide first react with PPH3. Okay, that's the triphenyl substituted phosphorus, and then we're going to have butyllithium, okay, in the system to form the Wittig reagent. Okay, the first step of the reaction is going to be an SN2 substitution, so the primary halides are more easily made into Wittig reagents than secondary halides. This is just an example of how the reagent is formed. I'm not going to require that you guys know this mechanism specifically. Just know how the Wittig reagent it is generated. So understand that the Wittig reaction is particularly useful because it installs specifically a carbon-carbon double bond at a specific place, meaning the carbonyl carbon. Now, understand that this reaction is also stereoselective. Using a Wittig derived from a simple alkyl halide is going to give rise specifically to the Z alkene when it comes to the product. So keep in mind that the major product, whenever we have a simple alkyl halide that was the source for creation of that Wittig reagent, is going to produce the major product of that alkene being the Z conformation or cis. But if the Wittig reagent contains an electron withdrawing group, okay, as you can see here, we have an ester motif, then the major product for the reaction is going to be an E, in other words, a trans alkene. So as you can see specifically here, we have two examples. Our Wittig reagent in the top part is going to contain an ester motif. That's why the major product is the E configuration of our alkene. In the bottom example, you can observe that here we're going to have our benzene ring specifically present in that Wittig. And again, whenever we have an electron withdrawing group in our Wittig reagent, remember the stereoselectivity that we're going to have for the product. Continuing on, the next reaction that we are going to discuss is going to be the Baeyer-Villiger oxidation, which understand that in this case we are going to insert an oxygen onto an aldehyde or ketone, okay, in between the carbonyl carbon and the neighboring alkyl group. So as you can see, this means that during this reaction, we can have an aldehyde or a ketone being converted to a carboxylic acid or an ester, respectively. So, as you can see here, if R, and I'm just going to distinguish them, R prime and R. If R is H, then understand that we are going to make an aldehyde, sorry, not an aldehyde, a carboxylic acid. As a product, while if R is alkyl, then that's how we form the ester in the product. Because remember that the motif for carboxylic acid is going to be a C double bond O OH, while for an ester is C double bond O O R. When it comes to the mechanism of the reaction, as you can see, for the Baeyer-Villinger oxidation, we're going to have a peroxy acid function as a nucleophile and attack the carbonyl. Then we're going to have a proton transfer from one location to another. So this is going to be an intramolecular proton transfer. And this is going to develop, as you can see, a 5-member ring transition state. In the next step of the reaction, the negative oxygen atom is going to then move the electrons down, is going to reform the carbonyl group, and we are going to be kicking off, okay, that peroxy acid motif that was incorporated in the first step, okay, and understand that in addition, we're going to have at that point the migration of that alkyl group or that hydrogen, depending on what we have, okay? And understand that as a side product, we are also going to form a carboxylic acid. Now, when it comes to the Baeyer-Villinger oxidation, but if we have a cyclic ketone, understand that because our ketone is specifically cyclic, what that is going to produce is a cyclic ester, and a cyclic ester specifically is known as a lactone. For an aldehyde or an unsymmetrical ketone, again, the rate of migration goes as follows. As you can see, hydrogen is going to be higher than tertiary, higher than secondary, phenyl, then primary, then methyl. So understand that you have to use this trend to determine the regioselectivity for that oxidation specifically. So let's look at an example specifically when we are utilizing the trend. On the top example, we have a ketone. On the bottom example, we have an aldehyde. So in this oxidation, as you can see, we have a peroxy acid. In the case of the ketone, as you can see, specifically, we are going to have the migration, okay, of the oxygen happen at the more substituted side. So if we highlight the atoms, understand that the migration or the formation of that ester is going to happen specifically on this site, because that is going to be the more substituted side of the ketone, okay? But in the case of the aldehyde, understand that it's going to result in the formation of the carboxylic acid because the oxygen atom is going to be attached to this side of the molecule. So understand that this trend is what determines where is that oxygen going to be specifically placed in our compound. This last slide gives you an overall view of all the reactions that we have explored. So if you need to make note cards in order to review every single one of the reactions that were explored in this chapter, as you can see, the summary is given in the following slide.